Yeah. Suppose we want to deal with surface area of revolution 8.2, and we have a curve from A to B. Let's say this is y equals to fx. Okay, and we want to revolve this around the x-axis. So I revolve this around the x-axis. It looks like this. And revolve this with respect to the x-axis. It becomes something like this. And the question will be, find the area. We want to find the surface area of revolution. What will the formula be? Okay, the way we approach that is by first taking a strip from that curve. Okay, let me get this one here, and I will zoom this out. I will zoom this out to be like this. So you see that the base here, the thickness is dx. Now this guy is not dx, this is ds, where ds is square root of dx squared plus dy squared, the differential notation. Now ds is the change of x squared plus the change of y squared. Okay, do you see the triangle? This is the dx and this is the dy. Okay. Now, then we will rotate this. We will rotate this around around x-axis. So what will the radius of this rotation be? The radius of this rotation will be y, right? Okay, the radius will be y. So the circumference of this rotation, or revolution, I should say, will be 2 pi y. Okay, now imagine, let's see, what ds, by the way? Not yet, just a circumference. I'm talking about the length of this here. Just the length of this. Just the length of that. Okay, that's 2 pi y. Now, so if I imagine the paper or the band that I go around now, okay, then what will the area here? Let me use different color. What will the area here? Then the area will be, yeah, that's approximately the area of a band like whose base is 2 pi y and the width is dy. Okay, so the area here, to be more precise, that's the D area. The D area, okay, because it's the area so small, right? Okay, is basically the circumference multiplied by ds. So imagine if that band, you spread it out. If you spread out the band, the height of that band is ds. Okay, the base of that band is 2 pi y. Right? So the area of that will be 2 pi y times ds. Okay, I use d there, the differential of area, because this dx is very, very small. It comes from this very, very small dx here. With this dx, we get the ds, and therefore we get the area of this band. Now, the surface area we are looking for is actually the sum of all such band. From A to B. From A to B. Okay. In this case, because we want to find the area of revolution around x-axis, right? Now, but when we add differentials, the notation when we add differentials is integral from A to B of 2 pi y ds. Okay, now notice that the x, the A and B here are in terms of x, right? And you know that that's a violation, because if you have A and B here, that's supposed to be the variable you use there, right? So you see that this formula is not appropriate. Okay, this formula is not appropriate. Now, how do we play with that ds then? Ds again is square root of dx squared, differential of x squared, times a plus differential of y squared. Now, if you need dx outside, okay, what you can do is you factor the dx squared. And it comes out to be square root of 1 plus dy dx being squared. And square root of dx squared is just dx. Okay, now again, I said earlier that these notation are not appropriate. I need to fix it, right? But the fix we need is just substitution. A, B, 2 pi, the y is a function of x, right? And then square root of 1 plus y prime being squared dx. Oh, I try to slow down. That's why, yeah, I get Shane is actually making a comment here. Let me share with you his comment. Yeah, I try to slow down because again, the nice thing about having those videos already up there, then it basically move a lot of lectures to that video, and I have more time to do more problems. And right now I have more videos, more explanation here. Okay, now the last one is the proper notation. Yeah, the last one is the proper notation. Maybe if I fix it even a bit more, it's supposed to be f prime x being squared here. Okay, that's a more appropriate notation. Now, that's if you revolve around the x-axis. Okay, focus not on memorizing the formula. Memorizing the formula is easy. You don't need to memorize that because in your test you have open book, open note. Okay, pay attention to how to set it up. It's more important. It is more important for you to learn to set it up. Okay, because if you just memorize the formula during the test, you will get confused which formula you should use. You see what I mean? Okay, while if you know how to set it up, then it's actually quite easy to recall. Oh yeah, this is the formula I need to use. This is the formula I need to use. Okay, now let's see the second case. The second case, I'm going over this with you because I know you can understand and set it up yourself. Okay, one of the biggest weakness of those students coming to my Calculus 3 is they don't even know how to set up the integration. Some little story. I have a student who took my beginning algebra, Math 115, many years ago. She got an A. He got an A in my beginning algebra, Math 115. And he's a good student, don't get me wrong. Okay, and then he took 125 with another teacher, and then 241 with another teacher, 260 with another teacher, 261 with another teacher, 262 with another teacher, and in 263, he took me again. So he actually did a lot of classes with other teachers, and later on I found out none of them good teachers. He purposely chose easy teacher to keep his A's. But then, strangely, he was there enough to take my Math 263, Calculus 3, which is your next class. Okay, and in between, I figured out that he had a calculator TI-92, I think. TI-92 is very powerful calculator that can do integration for him. You know, okay, and he asked me, Thomas, can we use calculator in this class? I said, yeah, go ahead, use calculator. I didn't know that calculator can do integration. I mean, nobody expect any student to be rich enough to use TI-92. Okay, that's an expensive calculator, by the way, very expensive. You know, it's very powerful. Now the thing is, then that's the reason he could pass Calc 1 and Calc 2. In Calc 3, however, I give you a problem in which you need to set up the integration yourself. Okay, and it's 3-dimension. Now, he didn't realize that his calculator can only do 1-dimensional integral, single variable, one integral sign, only one integral sign. The calculator cannot do 2 integral or triple integral. Now, the thing is, he depends on that calculator already so much such that he took my class twice and still failed the class really badly. Instead, the second time he took my class, I told him, hey, you know what? Don't depend on that calculator, Thomas. I don't know how to do it other way. It's like, well, okay. You don't know how to do it the other way. So how about learning it the right way? It's too late. I'm already in Calc 3. You know what happened? He can never go to engineering field anymore. He could never transfer as an engineer major. He could not even transfer as physics or math major. Indeed, he ends up in biology major. And he can say that, oh, I'm now in biology major. I'm proud I will be a doctor. And then I look at him, I say, no, that's not what you want to do at the beginning. The reason you go to a medical school, I mean, not to look down on medical school, but the reason you go there in your case is because you cannot do Calculus 3. Okay? Not because that, oh, I'm so proud I end up with, it's like, Thomas, would you mind not to say that in front of my girlfriend? Okay, now notice how bad it is that he basically, his teacher let him pass 261, 262, and those teachers earn the prestige of being good teacher by him. And he said, oh, these are good teachers. Why? I passed them. Oh, so Thomas is a bad teacher because Thomas failed you. In fact, Thomas is so bad such that you change your major because of Thomas. Don't you think so? No, I refuse to take that because he set himself up for failure and those teachers don't care enough. Okay, you want to blame the teacher? Too bad. There are some teachers there just for paycheck. No, I'm not that kind of teacher. Okay, but I don't blame those teachers. Okay, I don't blame those teachers. Okay, I'm saying that I'm here for you. That's why I tell you, no, don't depend on that. Okay, your brain is strong enough such that I know I can teach you that. Of course, I cannot change you if you don't want to learn it, right? But I need to warn you ahead. Who knows, in one day you need to change your major because you don't want to learn something and regret that for the rest of your life, right? Okay. Now, the second case, what if, on the other hand, we want to revolve the curve instead with respect to the y-axis? So this is my A, this is my B. Okay, and then this is my strip here. Let's say this is my strip. Okay, but I want to revolve it this way. Okay, I want to revolve it that way. So at the end, the curve will look like this. The surface becomes something like this. Now, then let's take a look on this strip here. Okay, let's take a look on that strip. This is our ds, right? Okay, and this is our radius. Okay, you tell me what is my radius equal to in this case?
X.
That will be x. Okay, so the circumference, once you revolve that around the y-axis, the circumference will be will be 2 pi x, right? Now, what happened is not only you have that circumference, consider that like a base of a cylinder. Now you also have that part of that curve that you rotate. Now, then what is the area, differential area of that surface? That will be 2 pi x times ds. Is it right? Now, the surface area, therefore, surface area therefore equals to sum of all such bands from x equals to A to x equals to B. That will be integral, supposed to be A to B, right? Let me write it down first, but this is x though. This is x equals to A to B, 2 pi x ds. Now, like what I said to you before, that this is not an appropriate notation. Actually, some instructors allow you to use this notation, like the variable of integration is not x, but the limits of integration in terms of x, as long as you write the x. As long as you write x equals to A, x equals to B here. Now, some instructors allow you to do that. Okay, how about you yourself, Thomas? I'm okay, I don't mind, you know, okay. But it's definitely not A only or B only while the variable of integration is S. Okay, now let me continue. Surface area equals to integral a to b, 2 pi already x, I don't need to change it. And then I need to change the ds though. That's square root of 1 plus dy dx being square. This is square here. Okay, now in fact, this notation is actually quite what you call that, flexible. ds equals to square root of dx squared plus dy squared. And I purposely use that notation here and also my lesson. Our textbook doesn't use that notation. Our textbook explain this section in a lot longer way. Okay. Now I'm not explaining it shorter. No, I'm actually explaining it with some verbal help, such that I don't need to write it down, right? If I write it down, it will be longer. Now, earlier I show you how we modified this ds notation into 1 plus dy dx squared, but that's because you factor the dx out, right? Now, if you end up integrating respect to y later on, then you need to have the dy out, right? If you integrate with respect to y, you need to have the dy out, and therefore modification inside is dx dy squared plus 1 under square root. Okay, so instead of factoring dx out, you factor the dy out. And in the next chapter, chapter 10, as I remember, you will have something called parametric curve, where you factor dt out. T is x is a function of time t, y also a function of time t. Okay, now all of this actually coming from here, and it has 3 different variations. Okay. Now, our textbook does not use this notation anywhere because it's not usable. Now, we cannot use that at all. When you have a single one integral sign, okay, then you must have one variable differential, right? Either dx or dy or dt. You should not have dx dy in one integral. If you have double integral, yes, it's okay. You may have the dx dy, right? But if you have only single integral, then it's not right to have 2 differential there. Now, then what we did is we modified this differential into the type that we need. Okay, so we will see this ds a lot. Okay, and I hope it helps us when we try to figure out we try to set up the integration once we do the revolution, and actually for other thing also. Yeah, actually for other thing also. Okay, now let's do problems from our book. (8.2) would you like to propose any question you would like me to do? Hey, anybody? I don't want to do easy problems. I do number 7 then. Why number 7, Thomas? It's odd number so that I can check the work, right? Okay, but Thomas, if you do all odd numbers, then we have no even number to work on. Now, I will not do number 19 because it requires us to do the approximate integration. That's a section I skipped before. So no, I will not do that one, number 19. Sorry. Unless I teach I go back and teach 7.7 or 7.6. I don't remember precisely. Number 7 first, and while you are waiting, so we have the curve given by y equals to square root of 1 plus 4x. And the x is from 1 to 5. Okay, and then we revolve around x-axis. Rotate around x-axis. Let me imagine that first. Let's say this is the curve. Okay, so this guy is the radius, that's the y. Okay, and the length there is ds. I rotate that this way. Okay, so the circumference is 2 pi y. Then the differential of the area will be that guy times ds. Okay, so the surface area will be integral from 1 to 5 of 2 pi y times square root of 1 plus derivative of that dx, right? So let's find what is the derivative of that y first. So solution y prime equals to 1 over 2 square root of 1 plus 4x times 4, which is 2 over square root of 1 plus 4x. Now, if I square it, then I get 4 over 1 plus 4x. Hey, you know what? Let's do this magic. I just multiply that in. So this guy times 1 is this, right? You see? So that's 1 plus 4x plus, now this guy times this equals what? Equals 4.
I have a quick question, Thomas.
Uh-huh.
Sorry, can you explain how you got the 4 over 1 plus 4x again?
4 over 1 plus 4x. 4 over... Oh, this, when I square it, because that's y prime squared.
Oh.
Right? I square it. So that's 4 over 1 plus 4.
Got it. Thank you.
And then that's equals to integral. I pull out the 2 pi. Well, from 1 to 5 of square root of 4x plus 5 dx. And then we do u sub, of course. Every time we see someone ugly. Okay, so this is 2 pi integral from 9 to 25 u to the power of 1/2 du over 4. So the surface area will be pi over 2 times 2 over 3 u to the power of 3/2 from 9 to 25. That's pi over 3 times 25 times 5 minus 9 times 3. It's supposed to be 25 times square root of 25. A to the power of 3/2, right? I mean, u to the power of 3/2. It's supposed to look like this. Okay, so I get pi over 3 times 125 minus 27. So that's 98 pi over 3. That's for number 7. Somebody proposed number 16 earlier. Let's take a look. Number 16. The curve is given by y equals to 1 over 4x squared minus 1/2 ln x. And this x is from 1 to 2, but you rotate around y. Rotate around y-axis. Okay, let me imagine. So let's say this is the coordinate system. This is the curve. X is from 1 to 2. From 1 to 2. So this is the ds, and I need to rotate it around the y-axis. So the radius will be x. This is ds. Circumference is 2 pi x. Then the surface area will be integral from 1 to 2 pi x ds, which is square root of 1 plus y prime squared dx. Okay, that's what we need. Now then, what is y prime? That's 1/2 x minus 1 over 2x. So y prime squared will be 1/2 x minus 1 over 2x squared. That's x squared over 4 minus 1/2 plus 1 over 4x squared. Is it right? Now then, if I add 1, yeah, don't rush into the integral. There'll be 1 plus that expression. But that's basically x squared over 4 plus 1/2 plus 1 over 4x squared, which can be rewritten as x over 2 plus 1 over 2x squared. So then this will be integral from 1 to 2 pi times x times the square root of that square. So x over 2 plus 1 over 2x dx. You know what? This becomes quite Mickey Mouse. Let me just distribute it. I actually pulled the pi out, but I used the 2 to make it x squared plus 1 dx. Okay, so this will be equal to pi times 1/3 x cubed plus x from 1 to 2. That's 8 over 3 plus 2 minus 1/3 plus 1. 7/3 plus 1, that's 10/3. So 10 pi over 3. Okay, now let me show you an interesting question. For example, let's do number 12. Number 12. Why is it interesting? Well, it's just simply new. We have a curve that is given by x equals to 1 plus 2y squared, the y between 1 to 2. So we have this curve here. Okay, but it's on y. This is 1 to 2, right? Okay. And the function is x equals to fy. So x as a function of y. Now, when you rotate around x-axis, it will look like this later on. Right? Okay, so the radius will be this. This will be the radius. This will be the radius. And this is the ds. Now, what is the radius? Radius is y, right? Now, do we need to change that to in terms of x? No, no need, because we will integrate that along y-axis instead. You will integrate that this way, not this way. Okay, so think of that as if that your x and y now change role. So the surface area is now equals to integral from 1 to 2 to pi y, that's the circumference. Okay, square root of dx dy squared plus 1 dy. You see what I mean? Now let's see what is dx dy. That is 4y, therefore dx dy squared will be 16y squared. That's 16y squared plus 1 dy. Am I too fast? Can you finish it yourself? Do you think you can finish it yourself? Okay, let me ask you this. What is my next step? You tell me what's the next step. If you get it right, then I'll let you do it yourself. I already give you the answer.
I mean, you're already doing it, yeah.
Yeah, you use sup, but use up what?
Use up the in the square root and the radical. 16y squared plus 1.
Okay, and then you go on from there, right? I don't think you should use trig substitution. Okay, can we do a trig substitution, Thomas? I think you can. It's just like simply because you can do it doesn't mean you want to do it, right? The reason I do use up here because the du has something y dy. So later on, this part will be absorbed by the du. You see what I mean? So du equals to 32y dy. So y dy later on will be substituted by du over 32, like that. Okay, now you do it yourself from there. Now, let me ask you to do one problem from there. What if I ask you to do number 15 maybe? Now, number 15 is even odd number. How about number 14? Number 14. So the curve is given by y equals to 1 minus x squared, where the x is from 0 to 1. Rotate it around y-axis. Actually, let me challenge you further. Consider that part A, number 14a. Just set up the integral, don't need to solve it, just set it up. And part B, what happens if you use the same curve, but you rotate around x-axis? What will the setup be? How many minutes? 4 minutes for each? No, too much. Yeah, okay, so 8, 10. Yeah, this is what I get, but if you go around y-axis, the radius is x. If you go around x-axis, the radius is y. But both of them has ds.
Oh, okay. So I just put in y instead of substituting the y value in. And for the x value, I thought that my initial thought was to maybe get the value for x. So to isolate the x and the y equals 1 minus x squared, but you just leave it as is.
Yeah.
Huh.
Because your variable of integration is in terms of x, right? So everything in terms of x. If it's already x, we are good. If it is y, then use that function.
Okay, got it. Thank you.
Okay. Now, as you can see here, oops, I'm way ahead. Okay. Does it matter which side of dy dx squared we put the +1? No, it doesn't matter because addition is commutative. So you can write 4x squared plus 1 instead here and you are still fine. Okay, yeah. The first one is quite easy to integrate. You just use u sub, right? The second one, I don't think so. This one, you need to use trig substitution, I believe. In fact, let me try to do this one. So number 14a, the question from the book, that's Mickey Mouse. Do you agree?
Yes.
Okay, now let's do the hard one. I like it hard. I miss Dorlene today. I separate them first because I'm afraid I cannot do both of them at once. 2 pi x squared square root of 1 plus 4x squared dx. So I will do theta x equals to 1/2 tangent theta. So dx is 1/2 secant squared theta d theta. Therefore, this is 2 pi, that will be what? Secant theta times 1/2 secant squared theta d theta. And the limit of integration will be when x equals to 0, the theta is 0, When x equals to 1, the theta will be tangent inverse of 2. Is it right? 1 equals to 1/2 tangent theta. So 2 equals to tangent theta. Right? That's how I get this one. Minus integral from 0 to tangent inverse 2 of 2 pi times 1/4 tangent squared theta secant theta secant squared theta d theta over 2. So on the first integral, the pi can come out. This is integral from 0 to tangent inverse 2 of secant cube theta d theta. Oh, we have formula for that, right? Okay, and then minus pi over 4 integral 0 to tangent inverse 2 of tangent square theta secant square theta d theta. Oh, should I make it tangent? This is make it secant cube. Okay. Then from there you go on. Honestly, I don't know how to do that one. The first one is easy. We have formula. The second one, iffy. But you think about it. Okay, you think about it. You took the test already, right? Okay. We are basically done with this section. Let me see. I have a chat coming in. How did we know to put the 1/2 in the trig sub? Here, because I want to kill that 4. Okay, 1 plus 4x squared, right? Now, we want this to be 1 plus tangent squared theta. Is it right? Okay, so you want your 2x to be tangent theta. Does it make sense? Therefore, we choose x equals to that 1/2 tangent theta. Yeah, so that we can fit the picture. Okay. I have to be honest with you that when it comes to integration, you need to be very sneaky. You need to be very sneaky. So when you practice with integration, you basically practice how to cheat here and there. Now, it's not really cheating. It's just like how to massage such that it looks like what we need. Okay. Now,
Hey, Thomas.
Yes.
Do you have any tips on, I guess, like learning to massage better, manipulate the functions a little easier? Because that's something that I have trouble with.
You do a lot of practice, and when you get stuck,
Okay.
you get help.
Okay.
So you see, usually the one you get stuck is like you don't know how to go on, right? Okay. Now then, in that situation, you take the picture, send it by email to me. Then I will tell you the next step. Okay. Use this substitution, and then I give it to you like that, and then you finish it. If you get it, good. If you still get stuck somewhere, then you come back to me again.
Okay.
Okay. So it will feel like this though. Some students don't like me doing that. But you know me already, Shane, so I don't expect you to hate me for that. So, so if you get stuck somewhere, I help you on that one point only, one part that you get stuck. So I give you, basically, if you get stuck somewhere, I tell you what is the next step. Only the
Okay,
next
that's
step.
helpful. Right.
Only the next step. Okay, and then you go on yourself. If you get stuck again, and you come back again, and then I tell you again what's the next step. Okay, now eventually these next steps are things that you internalize that you can go on yourself. You see what I mean?
Got it.
Yeah, it's not something we get. It's not something we get easily, though. I mean, how to say that? Somebody can be smart but still need help when it comes to those kind of things. You see? Okay, so yes, that's why group study is very helpful. And I say group study because the hints that you usually need are actually just simple hint that you don't expect. I say, oh yeah, we can do it this way. You know what I mean? It's like, oh yeah, those little things. So when I study together with my friends, did I share with you guys how I did my undergrad when it comes to study together, the group study? Now, if for those people who went to West LA College before, you must have seen that most of, if not all, of math classes have a lot of whiteboards. Yeah, have a lot of whiteboards. And that's because of me. Okay. My original intention is when they hire me, they want me to be the trainer for students. And I share with them that when I did my undergrad, the way we study is really a lot of group study. And in my undergrad, my university, we have a study room. The study room is very big. That's a room that you can put around 40 people on the sides of the room. Now, I mean, our classroom has 40 people you put in the room, right? No, this is 40 people on the sides. So the room is really big. The room is really big. Because the room is really big, you feel you are very small and becomes not significant. Why is it important? Then you don't feel that you are getting other people's attention. You don't feel shame or embarrassed if you cannot do a problem. So it has some psychological effect in that. Now, the thing is, you are not alone. There are a lot of other students there. And if you get stuck, most likely other students also get stuck. That reduce your embarrassment even further, which is not supposed to be. So what end up happening is me and my classmates, mind you that in Indonesia, the way we take classes is not like here. It's not like here, in the math department, for example, or basically you take different classes from your classmates. But in my math department, we tend to take same classes. So me and my classmates tend to share to take four same classes together. All of us, all 40 of us. So these 40 people basically get stuck together for at least 4 years in this department, study together. We become like brother and sister. Yeah, you know that I came from Indonesia, right? And most of Indonesians are Muslims. So I'm very, very good friends with a lot of Muslims. Most of my friends are actually Muslims. The one really, really good with me. Okay, so anybody who try to say talk shit about Islam, Muslim, I will talk to them, you know, because the true Muslims that I deal with in Indonesia are peaceful ones. Well, anyway, coming back here. So imagine the situation where each one of us not embarrassed to each other anymore, and we just ask each other, okay, even if I can do the problem and finish it, I still can walk around and see what my friend's doing. I don't need to ask them, can I see your paper? Can I see your paper? No, they actually do it on the board. So I can just walk around and see what they do. And when I walk around, I can see, oh yeah, that's right. You can do it this way. Oh, you can do it that way. You know, okay. You can be smart and still get stuck on problems that other person who is not that smart can solve easily. Yeah, I'm recording this. I want you guys to know that the way we do group study is supposed to be like this. The group study is not supposed to be like this. Like I go to the group meeting because I don't know how to do a problem or some problem. So I go to group meeting because I need help. If I know how to do all the problems, I don't need to show up. That's a wrong attitude. Group study is supposed to be a place where you go there, even if you know how to do some problem, you still go there and try to find out if other people do it differently. Is there any better idea to do this problem? Okay. Yeah. Now the thing is, I know a lot of students at West LA College, East LA College, Santa Monica. They only get group study once they get stuck. So you get good group study full of people who get stuck. Do you think you can help each other if all of you get stuck? No. If you wait until that time, right? Those people come to group study only those who get stuck. Those who knows, they don't show up. That's because of what? The mindset that you go to group study only to get help. No. The mindset's supposed to be you go to group study to help each other and to get new ideas to do problems, even though you know how to do that problem yourself. Okay, I hope that's a good insight though. Once you go to graduate study, especially, you will see most people actually think that way. Okay, graduate study, a lot of group study. A lot of group study. Now, let me do one more problem from this, from this 8.2. Problems that I don't really do in other class. Let's try number 31. See, I don't have this time if I don't have that recording. Okay, if the curve y equals to fx, so this is very theoretical, huh? Where x is between a and b, is rotated about horizontal line y equals to c. So you have this curve, let's say. Okay, let's say this is the curve. Let's say this is a curve, and you want to rotate that around the line y equals to c. Oh, I don't want to have two c's there. Call this curve. Find the formula for area of the resulting surface. So if you rotate this around the y equals to c line, you're supposed to get this, right? Okay, now can you find the surface area? Okay, where fx is below c. Yeah, that's right. I happen to draw it correctly. So the curve is below that line c. And how do you do that? Okay, let's see. That will be from A to B, right? Let's take a ds. This is the ds, right? This is the ds. This will be the radius. Now, what will that radius be? Radius will be c minus y. Is it right? This is y. This is the height. Usually we rotate around y, around x-axis, so we use y. Now the radius is not that one. The radius is here instead. Okay? Does it make sense for you? So now the circumference will be 2 pi times radius. Now how about the surface area then? Then the surface area will be integral from A to B, the circumference ds times the length ds, right? But that ds supposed to be in terms of x, so that 1 plus dy dx squared dx. Okay, where y is a function of x. That's the setup. So you see, it's kind of strange, huh? If you rotate that around x-axis, it actually looks like this. Right? Now, if you rotate that around another line, then it looks different. Okay, now that's for this 8.2. Let me go on to 8.3. There are two parts in this 8.3. 8.3 consists of part A on hydrostatic force, and the second one is center of mass, mass and center of mass. Mass and center of mass. Now you tell me which one you want to do first. I don't think I can do both of them today. B, mass and center of mass. Yeah, I cannot do both of. I don't think I can do both of them today. I mean, I can do both of them today, but I don't think that would be great. If I can, they're independent though. They're independent. You can do either one. They are not related, basically. Let's do A first. Okay, let's do A first. Yeah, I thought A is harder also. Yeah, that's what I have in mind also. A is harder. Yeah, A is harder to explain the theoretical foundation. Okay, but once we are done with the theoretical foundation, it's actually not too hard. Hydrostatic force. Okay, we start with the following situation. Suppose we have a pool of water in a box. In a box, we put water, and it doesn't have to be water. It's just anything fluid. Okay, anything liquid. Now, we are interested in finding the pressure at the bottom. Okay, what is the pressure at the bottom? Now, the pressure is equal to the force divided by the area where you apply the force on. Oh, by the way, this actually applies the same way with our daily life. What is the reason you feel a lot of pressure? Because you are carrying too much weight. Not body weight, I mean your responsibility, your obligation may be too much. You put too many things in your plate, while at the same time, your area, the room where you can move is too small. Okay, that's why we use a nail, right? Because the tip is very, very small. So you don't need a lot of force to push on that nail to make a hole. Does it make sense? So there are two reasons why you feel a lot of pressure in your life. Oh, suddenly I bring physics and math into daily life. Only Thomas can do that. Why? You have too much burden, you have too many things that you need to do. But another reason is because you have so little thing you can do. What you need to do divided by what you can do, the ratio is way too big. That's why you feel a lot of pressure. Now, the reason we come back to school is because we want to increase our area. You want to do more things, right? Able to do more things such that you can take more force without increasing the pressure. Oh, that's a nice thing, right? Anybody ever explain this way to you? Oh, as I know, only Thomas can. Okay, so force equals, pressure equals to force divided by the area. Now, suppose this area here, well, I can just leave it as area. Now, how about the force? In this case, the force is equal to the weight of the water in this box. The weight of the water in this box. So suppose this box is full of water, right? Okay, and let's say this is the height of the water. Okay, so the force of the water is equals to the mass times the gravity. You can use the Earth gravity, but I will just keep it as a G later on. Okay, while the mass is equals to the volume of the water times the density of the water times gravity over the area. So far, are you okay? So force, basically the mass times gravity. The mass is volume times the density of the liquid or the fluid you use. And to go even further, volume in this case is basically the area times the height. Right? It's a box times density times gravity over area. Now you see that the pressure experienced by the bottom of this box due to the liquid, to the fluid that you put in there, is basically equals to the height
Thomas,
times
you have area twice.
Repeat again.
You have area twice. Is it?
The area cancels.
Oh, okay.
Yeah, the volume equals to area times height. Right? Okay, so the area cancels. So the pressure is basically the height times the density. Let me use this for density times gravity. Let me use G. In other words, from what we do here, we find out that the pressure of experience at any point actually depends on how deep that point from the surface of the fluid. It has nothing to do with the shape. It has nothing to do with the shape. It's about how deep it is from the surface of the water, the surface of the liquid. Okay, now next thing. That's the first important things. Second important things that the pressure is at a point is the same to every direction. In other words, let's say you actually swim, right? You swim or in the ocean maybe, or in a pool. Now, the pressure that you felt by your ears will not change either you turn your head downside or sideways, downward or sideways or upward. Okay, now let's say this is my ear, this is my head, right? And this is my ear. Okay, this is my ear. Okay, now the pressure that I experience, experienced by my ear will be the same either I stand up like this, as long as the depth are the same, or if I actually in swimming position, instead of standing position, in swimming position, the pressure will be the same as long as the depth from the surface of the water the same. Now, you know this is true. Okay, now, so what happened then? What happened then? The consequence is this. So later on, when we try to find the force experienced by the wall, not the bottom anymore, but the wall, the force experienced by the wall, it has something to do with the pressure or the sum of the pressure on each points there multiplied by the height. Okay, so the wall is vertical, right? The wall is vertical. Now, the pressure at this point is different from the pressure of that point. Now, but you may say, but Thomas, what it has to do with the fact that the pressure goes in every direction? Now, what I want to clear up is this, that simply because the water, the bottom of the pool is facing up, doesn't mean that the pressure only going down. No, the pressure also going this way. You see what I mean? The pressure goes to every direction, not only downward. Not only downward, to every direction. How do you prove that, Thomas? Actually, to prove that, it's very easy. What happens if you take the wall away? Can you answer that question? If you originally have water here, right? A lot of water here, right? And then you take the wall away. If the pressure only goes downward, then the water will stay. You see what I mean? Right? Just like if you stack the book, right? Books instead of water, not hydrostatic anymore, but books. Okay, the pressure experience of those stacks of books actually being experienced only by the bottom of the surface. Right? How do we know that it's not going to any direction, other direction? Well, because even if you put a wall here, okay, it will not change the shape of the book. If you take the wall away, it will not change the shape of the book. Right? I try to explain some physics in an easy way to understand, in a way that you can observe in daily life. Now, the thing is, we don't have that privilege. We don't have that situation when you have with fluid. Okay. In other words, if we come back, then we know this retaining wall experience some pressure. Okay, and it turns out that the pressure that they experience in this direction is the same to the pressure it experienced in this direction. And in fact, it is the same pressure experienced upward in every direction, basically. Now, that gives us the idea, okay, then if that's the case, later on, if I want to compute how much force I need to put on this wall to be able to retain the water in the pool. Now, what I teach you here becomes the foundation for us building a dam. Do I read it right? Dam or dam? Dam. Dam or dam? Like for electric, hydroelectric, right? For hydroelectric, right? Now, the thing is like, Thomas, can we just build a dam so high? Very, very high? Well, as long as the pressure at the bottom is not too big. right? What you don't want to happen is you build a dam so high, right? Okay, like let's say your wall is not like this. Now you will not see a dam whose wall looks like this. It will not be. The wall of the dam must be like that, or even like this, like trapezoid. Okay, what's the reason? If it is a rectangle like this, you are assuming the pressure experienced at this point is the same to the pressure experienced at this point, which is not true. Right? The pressure you experience at the surface of the water is of course 0. And the further you go deep, the deeper you go, then the pressure will be much higher. So if you have a retaining wall for that dam in that form of rectangle, the dam will break and it will break at the bottom. It will not break in the middle. No, no. It will not break at the middle. It will break at the bottom. That's why then for you, when we construct the dam, uh, uh, actually the other days I spent some time looking over the largest dams in the world, the 10 largest dams in the world. And I think the largest one right now is in Brazil. Right, the largest now is in Brazil. The second largest, I think, in China, the Three Gorges Dam. Yeah, but if you take a look on how they build their dam, it's actually, the wall actually look like that. You know, basically they know because this has to be really, it has to be really tall. So the strength, especially at the foundation and on, has to be really, really good. Otherwise, the wall may tumble because the force at the bottom is too high. Okay, now let's go back. That's, so you see then, yes, even when you have retaining wall for the water, you still have force pushing that wall so that your wall has to be strong enough. It's not like you stack, again, I use the illustration of books. It's not like you stack books on the top of each other. You don't need a wall to keep that in place. No, you just need the surface, horizontal surface to keep it in place. Now, that's not the same with water. Okay, now then how do we compute? How do we compute the pressure and therefore the force experienced by a wall? Let's say this is the surface of the water. Okay, and then this is the container. So imagine in 3 dimension, we have something looks like this. A throw maybe, okay, and then we put some water in there. Okay, now this is the side view, this is the side view. Now we want to find out how much pressure and therefore how much force experienced by this wall. Is it okay? How do we do that, Thomas? Then let's do it this way. Notice that the pressure for the same depth will be the same. So let's say the depth at point X, the depth is X from the surface, then all the points at the same depth will have the same pressure. Right? All those points at the same depth, D, E, P, T, H, at the same depth will be the same pressure. Okay, now then the force experienced by these points, all of them will be equal to, the force will be equal to the pressure times the area. Again, because pressure equals to force times area, right? 4 over the area. So force equals to the pressure times the area. Which area? The area of this very, very small strip. This very, very small strip here. Okay. That's the force experienced along that shaded region. I want to do more from there. We know that why the small strip? Because the length of this blue strip here is different from the length of this of this yellow strip later on. What I plan to do is later on I add all the forces from each one of these strips. Okay, so looking back, then the force will be equals to the pressure. What is the pressure again? That's rho g, the density times gravity times height. In this case, the height is x. Times the area. What area there? The area is the length of that strip times the thickness of that strip. But the thickness of that strip is basically dx. Okay, so the total force, so this is supposed to be df then instead, right? This one here. Then the total force of this wall that I marked in green, the total force must be equal to the sum of forces on all those strips. Because those are small strips, then we will use integral sign. Okay, rho g depth, which I used x earlier, times the length for each depth times dx. Now, time for us to do problems. Okay, let me do a problem from our textbook. In other words, our textbook used this problem. Example 1. Then I give myself a break after this. Example 1 from our textbook. Our textbook tried to explain things in very, very technical way. The way I try to explain it tends to be from how to set up the integral. Now we have this situation. We have a trapezoid shape of wall. The top is 50 meters. And the bottom is 30 meters. The height of that wall is 20 meters. And then they tell us that find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top. So the water is 4 meters from the top. The water level is 4 meters from the top. Okay. Now, I will do this problem in 3 different ways. Instead of only one way, like the way our textbook explaining it, I will do it in 3 different ways. Okay. Now, the reason I do it in 3 different ways is to show you the flexibility you have, and therefore later on, the wisdom you need to get when you choose which way to approach the problem. Okay. Now, our textbook use the surface of the water as their line of reference, they call this x equals to 0. Yeah, they call that their x equals to 0. Now then, so how deep the water will be? At the bottom, what is x equal to? If x equals to 0 starts from here, right? And then at the bottom, x will be equal to 16. Okay. I agree with you that we may call that negative 16. Okay. But you see that the x actually progresses that way. The x is not progresses that way. Does not progress upward. The depth is increasing downward. Right? So we're supposed to call this positive 16 instead of negative 16. Is it okay? Yeah, so yes, that's the positive negative becomes an issue. But the x increases as we go deeper. Right? So it's supposed to be positive 16 here instead of negative 16. Okay. The reason I point that out because it seems to be negative 16 because it's downward, right? Like from a number line y-axis, then that's supposed to be negative 16. Okay, but physically speaking, this x represent the depth, and the depth is increasing as we go further down. That's why it becomes positive instead of negative. That's an important notion though that I have to mention. Okay, I don't want you to think that every time we go downward, then it will be positive. No, that's not true. That's not true. It's because how we define our x. Okay, now for each x that we choose, let's say this is our x. Okay, now can we find what is the length associated to that as a function of x? Okay, so when I go as far as x meter down, what will the length be? What will the length be? Now, then from here, our textbook actually use a similar triangle thingy. Okay, similar triangle thingy. Our textbook does this. Let's say this is the length. Let's say this is the length. That's not good. Let's say this is the length here. Okay, now then the way they build it up is, I wonder how they do that. I don't really read the book though. I prefer to see it this way. I'm sorry, I cannot do it. I cannot do it long way if I know how to do it fast way. Okay, this is how I do it. Like when x equals to 0, what is the length? We don't know, huh? We don't know what's the length. But can you tell what's the length when x equals to negative 4? Here, when x equals to negative 4. The length is 50, right? When x equals to 16, the length is 30. You see what I mean? And you can tell from here that the length grows linearly as x grows, right? So think of this as a linear equation. Okay, the slope is 50 minus 30 over negative 4 minus 16. That's 20 over negative 20 equals to negative 1, right? So the length as a function of x is negative x plus some constant. Negative 1x plus some constant. So L, let me use that negative 4 comma 50 as the coordinate of 50 equals to negative of negative 4 plus b. So that's b equals to 46. So the length is equal to negative x plus 46. Once we know how deep we are, we know the length of that strip. Can you follow me? So the differential of the force at that strip will be rho g depth, that will be the pressure, times the area of that strip, which is length times ds. I'm sorry, dx. Rho gx times 46 minus x dx. So the total force will be integral from 0 to 16 rho gx 46 minus x dx. Okay, now in my class, and in my test, when I ask you to compute this, you can leave your answer in terms of rho g. So just get the numbers, but leave your rho g, the density times the gravity. Okay. Let me compute this then. This is integral of 46x minus x squared from 0 to 16 dx. That is rho g times 23x squared minus 1/3 x cubed from 0 to 16. That is equals to rho g 23 times 16 squared minus 1/3 times 16 cubed. Okay, you can use your calculator from there. Now, this is one way to do the problem. Any question? No question. Okay. Notice that what I would like you to focus on is to create this situation. For every depth at x, how deep you are, you need to find what is the length of that strip. You will see these questions, all the problems here boils down to this situation. Okay, for the depth of x, how deep will that be? Okay, how long the strip will be. Now, let me replicate what we have here. Let me copy this and do it with another method. Hopefully by showing you more than one method. Why it looks like that? Yeah, hopefully by showing you more than one method, instead of getting confused, you see the purpose of each one of them. Now, I will not do it this way. Okay, I will not do it this way. I will use my point of reference here, my line of reference. Instead of from the first surface of the water, I take it from the top of the water, x equals to 0 here. So what will this be? I don't start from the surface of the water, but I start from the top of the pool, the top of that container. Now the bottom will be what? Will be 20, that's right. Okay, but later on, when I integrate from the surface of the water, which is x equals to x equals to what? The surface of the water. x equals to 4, right? Now, later on, my integral for that force will be from 4 to 20. Okay? So think about this. If this is the depth, how deep we are, right? If this is our x, okay, then my x will start from 4, not from 0. Basically, we don't need to integrate starting from 0, even though that's the preference. Okay. Here I start from 4 because my level of reference is the top of the container instead of the top of the water. Now, going on, what is the force? What is the pressure? The pressure will be rho G. Well, how deep is the water when x equals to x, when the depth is equals to x? If this is the x, then the depth of the water at that point will be how deep it is. That will be x minus 4. Let me write it down. So this is the depth times the length, right? Okay. Not the depth in terms of x, but the depth from the surface of the water. This is integral from 4 to 20 rho G x minus 4. Now the next challenge is, what will be the length? Well, when x equals to 0, the length is 50. When x equals to 20, the length is 30. And then you do the slope thingy, right? Okay, you will see the slope is -1. And going further, you get y equals to negative x plus 50. Or the length, I'm sorry, the length. So this will be 50 minus x. You see what I mean? And from here, you will integrate. Okay, trust me, you will get the same result. In fact, I don't need to compute it in full to show you the same result. All I need to do is to do u substitution. U equals to x minus 4. If u equals to x minus 4, du equals to dx. My limit of integration will change from 0 to 16. Rho g, this is u, and this will be 46 minus u du. Exactly the same integral we have up there. See, right? Okay, so I don't need to compute that. I just need to reform that and confirm, oh yeah, they're the same, right? Okay, I will show you the third way after the break. The third way, basically, I use the same graph again. Let me copy paste that now. The third method later on will be doing it from the bottom. So instead of having my x starting from the top, I start from the bottom. So this is my x equals to 0, and this will be x equals to 16. Okay, So my x will grow from the bottom instead going up. This is my x. You see that? But let's take a break first. We come back at 9:15. Let's start. Now we have this setup here. We want to find when we have x here for given x, what is the depth? What is the length? And you notice it's always about the depth and the length for given x. Okay, our textbook purposely set the x equals to the depth pretty much all the time. But I want to show you that it's actually not necessary. It's actually not necessary. Okay, now then, if this is x here, if this is x here, then the depth will be, how deep will that be? The total has to be 16, right? So the depth will be 16 minus x. Is it right? Now, how about the length? Well, we happen to see that they behave linearly. When x equals to 0, the length is 30. When x equals to 20, the length is 50. And you can see, I do it fast. Basically, you will see y equals to x plus 20. Sorry, x plus 30. X plus 30. Now then the force will be integral from x equals to 0 to x equals to 16 rho g. The depth, which is 16 minus x, the length will be x plus 30 dx. How do we show that we will get the same answer, Thomas? Substitution again. Let u equals to 16 minus x. So du equals to negative x dx, right? Such that my integral will be, this will be 16, this will be 0, rho g u. That's, what is this? 16 minus u, that will be, so x equals to 16 minus u. So x plus 30 will be 46 minus u. Negative du. Okay, and I will absorb that negative by reversing the limits of integration. Done. So I already shown you that these three ways of finding hydrostatic pressure give us the same result. Okay. Now let's summarize the hint, the procedure summary. First, there are more than one way to set up the integral. Second, for given given X, what are, give me a second. Can you hear me? Yeah, I just get a message that my internet connection is not stable. Yeah, let me know if I suddenly lost though.
Everything was fine.
Okay, thank you. So, okay. So given X, what are the depth and what are the length of the strips? Okay, and third one, you will see that most of the time, I'm not sure if it is always, but so far I can confirm most of the time we can convert from one setup, from a setup to another setup by substitution. This is just a little note from me though, part 3, just a little note from me. So let's say you do the setup and then your friend, your classmate do get another setup, right? And both of you just like, you know what, I don't want to compute this. You know, I just want to know if my setup is correct. So you compare your setup and try to do a little substitution, see if you can get from your setup to that person's setup or the other way around. Like the way I did earlier when I tried to check if I will get the same integral. Okay, now let's do more problems. Those are just the same problem actually. Those are just the same problem. I do it with 3 different methods. And I hope you can see the essence, even though I see that question from 3 different point of views. But from 3 different point of views, we are staring at the same thing. What are those things? Given X, what are the depth in terms of X and the length in terms of X? Those are the keys. Okay, now let's see question number. Do you want to choose a question? Number 4, 6, 8, 10, or 12, 13, 14, 15. Number 12, okay. Number 12, a milk truck carries milk with density, so rho equals to 64.6 pound per cubic foot. In horizontal cylindrical tank with diameter 6 feet. So it is a horizontal cylindrical tank. So I hope you can imagine that, right? And then let me do the side view of this tank right now. It says that the diameter is 6 feet. The diameter is 6 feet. Okay, find the force exerted by the milk on one end of the tank when the tank is full. So we want to find the amount of force experienced by this tank here at one end of the force, one end of the tank. Okay, so now where should we put our point or line of reference? Now, see, we usually deal with the radius, right? Okay, so let's put our line of reference here. Okay, so this is our x equals to 0. Now, we will go, you can go up, you can go down either way, but either way, you will see that our x will be from -3 to +3. Is it okay? -3 to +3. Now, for any x that I choose, what is the length here? Now, the radius is 3. Let me grab that out. So if this is x, this is 3, this is square root of 9 minus x squared. Is it right? So given x, what is the depth? Notice that the water starts from the top. Okay, so how deep is this? If you have x from that line of reference, okay, then how deep will that point from the top of the water? It's x plus 3, that's right. That's x plus 3. Okay, then how about the length? We get it there. But this is only one side of the length though, half of the length. The length will be 2 times square root of 9 minus x squared. Okay, so then the force will be integral from -3 to 3 rho g. The depth is x plus 3. The length is of the strip is 2 times square root of 9 minus x squared dx. That's the setup. Okay, now I believe you can integrate that yourself.
Do we do anything with the actual number for density?
Oh, you can put that in later on at the
Okay.
very end.
Gotcha.
The rho g, even if you need to do it, you can do it at the very end. Yeah, the rho is given. The g has to be in feet per second square. Right? The units has to be conform. Actually, let's go on further. Do you know how to compute this? That's actually a good question, I hope. Rho g integral -3 to 3, 2 times x plus 3 square root of 9 minus x squared dx. Okay, how will you compute this? Okay, this is actually a side note. What I'm about to show you here is like has nothing to do with, once you set up the integral or anything after this is how you do your integration, right? Okay, I hope you realize that. Now, what I want to show you is how to be, I mean, before you really do your integration, be a bit sneaky, be a bit kind of like observe what you have before you just attack that integration right away. So some people, I have to say, some people in my calculus 2, not your class, not your class yet. I haven't seen your test 1, but in the past I have seen students who think they are smart. Okay, but the way they attack an integral is just like, man, why do you do it that way? Okay, what I want to show you here is like, notice that the limits of the integrals are opposite to each other, right? Now, if you can get an odd function, integral from negative a to a of odd function is equal to 0. I mean, you can try integral from negative pi to pi of x to the 5th minus 7x cubed plus maybe e to the 9x dx. You want to work hard? Go for it. Okay, but the way I will argue is note that x to the 5th minus 7x cubed plus e to the 9th x is an odd function. Therefore, the integral is equal to 0. Have you seen that before? Supposedly in your Calc 1, right? Yeah, you're supposed to have seen that. It's just like you have seen that before, but you didn't never really relate that to other work you have done. No, I want you to relate it. Those are important things to shorten our computation by big time, by very, very big time. Okay, now, but I don't see that here in this integral, Thomas. Actually, you do. Actually, you do. Okay, if you split this is 2 rho g integral negative 3 to 3 of x square root of 9 minus x squared dx. That's an odd function. That's an odd integrand. Plus 2 rho g times from negative 3 to 3 of 3, which I can just move it here, right? Square root of 9 minus x squared dx. Does it make sense? Now, this is equal to 0, the first term. Is it okay? And the second integral is actually still easy to do. I will just tell you the answer. This will be 6 rho g times 9 pi over 2. What the F, Thomas? You can do it so fast? Yeah, that's how good we are. You're so smart, Thomas. Yes, I'm really, really smart. No, you don't need to be smart for that. You need to be sneaky.
Wait, can you show us how you got that fast?
What is this?
I'm not sure what you're asking.
You still don't get it? I already graphed it for you.
No, I'm sorry, I don't.
Oh, okay, that's the area of semicircle with radius 3.
Oh. So all you did was see the graph of it in your head?
I happen to realize that we are dealing with the circles, right?
Okay.
Right, and then
right.
this is actually the top part of a circle. Okay, and we are lucky that this is from negative 3 to 3. If that were from negative 2 to 3, no, I cannot do this trick anymore.
I see. Okay.
Right. If it's from negative 2 to 3, that's not that's part of the semicircle. It's not computable. But here happens to be a perfect semicircle with radius 3. Okay, well, just like what is the area of that semicircle with radius 3? Okay, so you didn't expect me to do that trick, right?
I didn't know it existed.
It's I'm showing you this because we actually see that once in a while, and if this kind of question show up in your test, it actually becomes a place where you can Save a lot of time. When you do this problem, I still assume that you will do it long way. Like you will do x equals to 3 sine theta. You see what I mean? I expect that's what you will do, but if you actually happen to say, oh, you know what, that integral, interpret that integral. Try to interpret. So while your brain is running for how to integrate this, your sub-memory try to see, oh, what this means. Okay, otherwise you will spend a lot of time though to do this problem. So you see this problem, let me point out that if you try to do this problem as usual, it will take you a long time, at least 10 minutes, I think. Or let's say 5 minutes. But with my method, I break it up, like divide and conquer. I break it up into 2 integrals, right? One of them is tame, that's 0, boom. And I was lucky enough, we were lucky. I didn't expect that when I split it up though. Only after I wrote it down, I was like, hey, you know what? That's semicircle, the area of semicircle. Oh, nice. So suddenly a question that's supposed to be done in, let's say, 7 minutes, you end up doing it in 2 minutes at most. Okay, so this is equals to 27 rho g pi. Now let's plug in numbers. The rho is, just to check with the book. Oh no, this is even number. This is even number. So this is, well, then I cannot check that anyway. But yes, that's how we do it. Now, how about part C? What if, part C, what if the tank is half full? What if the tank is half full? So the tank is only here. The drink or the liquid or the milk is only half full. I think I will still use that line of reference here. Okay, x equals to 0 here. And you will see that our x will move from 0 to 3. Instead of from -3 to 3, it will be just from 0 to 3. So the force will be integral from 0 to 3 rho g x times 2 square root of 9 minus x squared. Because this is the, if this is x, that's the depth already, right? 9 minus x squared dx. Now the thing is, now we cannot do even odd function here because the limit of integration is not symmetric around 0. It's not opposite. They are not opposite to each other. So I have to do it long way. Yeah, so sad. Okay, so u equals to 9 minus x squared. Du is -2x dx. Okay, so my integral will be from 9 to 0 rho g. Oh, I have 2x dx. That's negative du. And this is u to the power of 1/2. Okay. Let's integral from 0 to 9 rho g u to the power of 1/2 du. That's rho g 2 over 3 u to the power of 3/2 from 0 to 9. Rho g times 2/3 times 9 times square root of 9 minus 0. That's 18 rho g only. Oh, no pi. Surprise. Any questions so far? Okay, let me do one more question. I don't really want to do that kind of question. Which question I would like? I would like to show you something quite important. Like let's say this one, for example. Suppose I have the wall of a pool has the top in semicircle. Okay, let's say that's the drain of that pool, a little chip there. Okay, and suppose we want to cover that. Suppose we want to cover that. Okay, so we are now interested in the hydrostatic force experienced by that door or that cover. If let's say the radius is r. Let's say the radius is r. Consider this just the first part of the question. Consider this only the first part of the question. So how much force needed so that the cover stay in place? Okay, otherwise the water will come out, right? Let's say this is full of water here. Let's say this is full of water here. Then how much pressure, how much force experienced by that yellow door, yellow cover, before it actually move and the water leak? Okay, we will start with, let's say this is our line of reference, x equals to 0. Then how deep will this be? There will be r, that's right. Okay, so our integral later on, our force will be integral from 0 to r, right? Rho g, okay, then if I move from x equals 0 to r, let's say this is my given x, let's say this is my given x, what will be the depth? How deep is this position here? The depth will be x also, right? And the length will be, the length of this strip will be, then you draw that. If this is x, this is r, what will this be? It will be square root of r squared minus x squared, right? But then you double the length. So this will be 2x square root of r squared minus x squared dx. That's the formula. Actually, we can go further. We can go further. I can go further doing substitution. We can solve this integral even though in terms of x and r. Actually, at the end, we will not have x, but we will have r. So let's do u sub u equals to r squared minus x squared. Du is negative 2x dx. That's integral from r squared to 0, rho g u to the power of 1/2 negative du. What happened to the r squared? Which r squared?
When you do the u sub and you find a
derivative.
Yeah.
R is a constant. So when you do the derivative, it becomes 0.
Okay.
Okay, yeah, it becomes 0. So then this will become, I absorb the negative by reversing the limits of integration. Okay, rho g u to the power of 1/2 du. So this becomes 2/3 rho g u to the power of 3/2 from 0 to r. I'm sorry, 0 to r squared. Oh, that's r squared. That's nice. So this is 2/3 rho g of r cubed minus 0 cubed. So just r cubed. That's it. Oh, nice. I'm not done yet. I'm not. Oh, this is 9:47 already. Oh, hold on, hold on, hold on. Don't go yet. Don't go yet. I said this is only the first part of the question. Now, what I want to show you is that what happens if I sink this cover by, let's say, some constant. Let's say by constant c. So instead, now we have a pole, and I sink that cover as far as, I prefer another constant, as far as a unit down. The radius is still 5, the radius is still r. Okay, the radius is still r. Now the question is, how much force being experienced by that cover by sinking that cover as deep as a units. And I want you to see that the result is actually quite nice. Our textbook does not talk about this. Okay, let's start in 7 minutes, maybe less. This is our point of reference. Call this x equals to 0. So with this window, with that semicircle, it goes to r. Okay, now when the depth, when this is x, given x, can you tell me what's the depth? How deep it is if the surface of the water is here. This is the surface of the water. How deep is the position x here? A plus x, that's right. That's a plus x. Now the length, however, is still 2 square root of r squared minus x squared, right? I mean, that's the same triangle we have. Right? This is x, this is r, this is square root of r squared minus x squared, and then you double it. Okay, so if we sink, we push that shape a units down the water, the surface of the water, or the surface of the fluid, in case there's not water, then the force will be integral from 0 to r rho g times a plus x times 2 square root of r squared minus x squared dx. Now, what I want to show you is the following. This is equal to integral from 0 to r rho g a 2 square root of r squared plus x squared dx plus integral from 0 to r rho g x2 square root of r squared minus x squared dx. Okay, copy that down first. Now, explanation. This is the force when the force before we sink it. That's what we have earlier. That's what we have earlier before we push that down. Do you see that? That's the force before we sink it, before we push it down. Now, but how about this guy? What is this equal to? Let me factor the rho g out, rho ga out. Notice that this is basically the area of the cover. That's the area of the cover. The area of that yellow region. Now, what I want to tell you is actually the following. So, suppose the force experienced by a wall is F, the force experienced by a wall is F, right, or region. This is the region. Okay, and the force experienced by that region is F. Then the force experienced by that region after pushing it further down by A units is the original force before you push it plus rho g A times area of that region. Do you see what I'm trying to say? So if you have that shape there and then you push it down by, let's say, A units, then what happened to the force experience at this place? That will be the same to the original force you have when you are yellow, plus the additional force you experience due to going diving even further down. And that force due to diving further down is equal to the area of that region times how far you go down times the density times gravity of the water or the liquid or the fluid you are in. Okay, now this will be very, very useful. Okay, let me stop here. I'm supposed to stop here. I believe you have the suggested homework from this. On Monday, then I will do the second part of 8.3. On Monday, I will do the second part of 8.3. And maybe after that, I go on to chapter 10. Okay, see you then on Monday. You're welcome.